Imagine you are trying to find the fastest route to your favorite coffee shop in the bustling city. But what if the streets were constantly changing and you had to navigate through them with limited information? In today's video, we are diving deep into Dijkstra's shortest reach algorithm, a powerful tool that helps us solve this very puzzle. How does it work and why does it matter? Let's find out. Alright, let's dive into the heart of the problem step by step. We are tackling the classic Dijkstra algorithm where which helps us find the shortest path from a starting node to all other nodes in a weighted graph. But before we jump into the code, let's build our understanding of the logic behind it. First up, we need to represent our graph. In this case, we use an edge class. This class is vital because it allows us to define the connections between nodes, specifying not just the destination node but also the weight of that edge. Why weight? Because it tells us how costly it is to travel from one node to another. Now, once we have our edges defined, we need a way to keep track of which node to explore next based on the shortest distance we have found so far. This is where our priority queue comes into play. Think of the priority queue as a waiting room where nodes with shorter distance get served first. By implementing this as a min-heap, we ensure that every time we dequeue, we are getting the next node with the smallest distance efficiently. Next, let's get into the core of the Dijkstra algorithm itself. We start by initializing an array to hold the shortest distance from our starting node to every other node. Initially, we set up all distances to a maximum value, indicating that they are unreachable until we find a path. The distance to our starting node, of course, is set to 0 because that's where the journey begins. Now, as we explore the graph, we'll maintain a visited array to keep track of which node persists. This prevents us from revisiting nodes and potentially getting caught in endless loop. Each time we dequeue a node from our priority queue, we check if it's already been visited. If it has, we simply skip it and move on. As we explore each node, we look at its neighbor. Those are the connected nodes we can move on. We can move to. For each neighbor, we check if the path to the current node offers a shorter distance than what we have recorded so far for that neighbor. If it does, we update the distance and enqueue that neighbor with the new calculated priority. This way, we are gradually refining our understanding of the shortest path. Once we have processed all nodes, we'll have the shortest distance from our starting node to every other node in the graph. However, we need to handle the output carefully. If the node is still marked as unreachable, we'll represent that with a -1 as per the problem requirements. Finally, let's not talk about the input. We need to read the number of test cases, the number of nodes and the edges themselves before we can run our Dijkstra function. This involves building a graph based on the input data, ensuring we correctly account for any duplicate edges by keeping track of the minimum weight for each connection. With this clear breakdown of the logic and structure, we have laid down a solid foundation, and now we can confidently transition into writing the code, knowing exactly how each piece fit into this intricate puzzle of the shortest path. Alright folks, let's quickly recap what we have covered so far. So we dove into the classic Dijkstra algorithm, which helps us find the shortest path in a graph. We start by creating an edge class to represent the connection between nodes. Then we build a priority queue using a min-heap to efficiently manage our node while calculating the shortest distances. Our implementation of Dijkstra algorithms takes us in the number of nodes, the graph structure, and the starting node to produce the shortest path of all other nodes. We even ensure that the graph can handle edges and varying duplicates and avoiding duplicate edges as well. The main takeaway here is that Dijkstra algorithm leverages the priority queue to optimize the path finding process, making it both efficient and effective. Remember, while working with graphs, understanding how to build and navigate them is crucial, and today's code gives us a solid foundation. Make sure to check out the source code in the description below. If you found this tutorial helpful, don't forget to hit that like button, subscribe for more coding content, and let me know in the comments what you'd like to explore next. Speaking of what's next in our upcoming videos, we'll tackle traversal methods like depth first search and breadth first search. Plus, we'll show you how to tackle some real world problems using this concept. So stay tuned and keep coding.